Hello there. You're all very welcome to this, the second in the series of webinars from Impedance. This is an educational webinar, and we say educational because we would like to learn as much from yourselves as indeed we hope to share with you today. So for that reason, I'd ask you to enter any questions you may have in the Q&A box, in the chat box here. And if we don't get to them by the end of the webinar, we'll certainly reach out to you in the next few days to answer the questions. And of course, we can also set up a one-on-one with today's host if you wish to have a more personal consultancy about your particular requirements. Other than that, there's no particular requirements today. Just sit back and listen and enjoy the webinar. But before we start, I have some good news to share about Impedance. Just in the past month, we're happy to announce that we've closed €3.5 million in Series B funding round. Now, what this is going to enable us to do, of course, is to continue that process of innovation that we're proud of here at Impedance, and we're going to be able to offer you a brand new range of products, additional features to the existing products. But of course, this all depends on the feedback that we get from the market and what it is you guys are particularly looking for. And we're just showing you briefly here on the slide some of the partners that have helped to take us to this next exciting stage in the Impedance journey. So I'd like to introduce you to our host, who today is Dr. Tom Gilmore. Tom holds a PhD in physics from Queen's University in Belfast, so just literally 100 miles from where our head office here is in Dublin. And he is our Chief Product Officer. He has extensive experience through the years in semiconductor fab equipment and also in plasma process measurement. So he has a lot of really interesting knowledge to share with you. And as I say, if you have specific information around the particular tools that you're using, Tom is the man to ask the questions to, and we hope he can make those answers for you. So Tom, it's over to you from now.
Fantastic. Thanks very much, Declan. I'm going to turn off my camera to conserve bandwidth and make sure there's no issues or technical difficulties while we go on. So I'm going to turn it off now. Then move on to the next slide. So, right. So what are we talking about today? So we're mainly talking about how ions behave in plasmas. So let me talk you through what we're going to cover today. So first, we'll just talk about ion energy measurements, kind of the importance for looking at what ions are doing to your wafer. I mean, I think it's kind of obvious, and what kind of challenges there are there to measure this sort of data. I'm going to introduce you to a technology that's called a retarding field energy analyzer, or ion energy analyzer. And I'm going to kind of introduce, how can I say, how you build one, what things you need to care about in order to get, like, accurate representative data from this instrument, so that you know that what the instrument is telling you is what the reality is when your tool is running. Of course, we're also going to help you understand the data from it. And then what I think is going to be most interest to everyone in this audience is, how do ions behave in different plasma conditions? So like if you, in your tool, change the pressure, change the gas, change the power on the top electrode, or change the power on the bottom electrode, or you use, you don't use 13.56 megahertz, you use something else. What does that do to the ions that are impacting your substrate? Okay, so we're going to show you lots of real data examples for this. Of course, I will introduce some of the commercial versions of these that Impedance made available. And then at the very end, I want to do something a little different. So I want to hold a kind of hybrid Q&A. So what do I mean by that? Basically, I have data from many different, commercially used tools, so Oxford Instruments tools, Applied Materials tools, and these sort of tools, and also from many kind of laboratory tools that are representative. So I have a whole set of slides with data examples from different plasmas, and I want to encourage people to kind of ask, like, say, okay, I have a tool. These are sort of the parameters that it has. Can you tell me a little bit about how ions behave in my tool? So if you put that into Q&A, I'll go to a slide which shows something that's most representative of what's in your tool. Okay. So let's get started. So let's talk about ion energy measurements. Why do we care? So obviously, ion energy measurements are kind of crucial for process development. So when you think of, your plasma processing your wafer, obviously what's really happening is, the plasma enables chemistry to happen. It enables particles to be ionized, and therefore you can control them with voltages. You control with electric fields. And then those ions are processing your wafer in some way. So, depending on the ion energies and the ion flux, which is the number of ions impacting your wafer per second, you're going to have different etch rates. You're going to have different film growth rates. You're going to have different thin film properties depending on the ion content. It's also important for other things like ion beam tools and plasma thrusters to understand, when I extract ions from this plasma and they then impact my substrate, what do they look like? Are they varying with time? Like if my chamber pressure is up a little bit, is that acceptable or not? This is what you learn with these. So in other words, what measuring ions allows you to do is to really understand and characterize what the plasma process is doing to your substrate. Which means that because it's such a direct measurement, it really enables like precise tool matching. You can really make sure that what the wafer sees in tool A is the same as tool B or tool C or the different modules, and also for process transfer between tools. So if you develop your process of one tool and you buy a new tool set and you want to now take measure, like run the same recipe there, are you going to get the same results? And this gives you direct visibility on that. Now, it's quite challenging to take measurements in plasma environments. Obviously, it's under vacuum. Typically, there's radio frequency there, so that causes another difficulty. You can have high temperatures. You can have, extreme chemistries that are etching away or deposition. So it can be quite difficult to build these sort of sensors. But anyway, ion energy analyzers do exist, and they can take measurements in these extreme environments. So let's talk about these ion energy analyzers. So firstly, I'm going to show you kind of what they typically look like from a very high level. Let me turn on my laser pointer. There we go. So what these things typically look like is, some sort of like wafer-like thing, something circular that matches the size of your substrate. It has some sort of aperture that can take a measurement, and this is placed inside the plasma tool where you'd normally place your wafer. And with the modern designs and the techniques I'm going to show you today, these are useful in DC and RF plasmas and pulsed RF plasmas and microwave ones and laser ones, pretty much almost any type of plasma. And later I'll actually show you kind of a chart of where it's applicable and where not applicable, where you can use this technology. These things tend to be a few millimeters thick, and this is sort of a cross section. And in this talk, we'll go into a lot of depth into what all this means and what all this is for. Well, let's start really basic. How do ion energy analyzers work? And I want you to just for a moment ignore most of this cross section of a sensor and have a look at this middle grid here, G2. So the key way that the way an ion energy analyzer works is ions come from the plasma. They go through some sort of aperture and allow the ions to come in. And then there's this grid here where you apply different voltages. But the idea is that, if this is at 0 volts, all the ions pass through. So I'm going to kind of show you on this graph here. So this is a measurement of the ion current coming in the sensor. So initially, lots and lots of current is coming in the sensor. And then what happens is you increase the voltage on this discrimination grid. And as you increase the voltage, you start to block the current. And as so you keep increasing and increasing and increasing the discriminator voltage, and eventually you get no current at all. And that means all the ions are being accepted at that point. And then essentially, this is telling you how many ions you have at different energies. So by doing the first derivative of this curve here, you get what's called the ion energy distribution function. So this is how many ions are present at what energies. So now this discriminator voltage, 100 volts, is now representing, an ion with charge 1 having an energy of 100 eV. And this is kind of a fairly typical distribution. Well, there's many distributions depending on the tool, but we'll get into that. So that's essentially it. With this technology, you can measure exactly how many ions you have at different energies and kind of what your ion flux is and these kind of critical things that drive the process. So let's go a little further into depth on what all this means. So what are the design considerations for these things? In other words, you need to make sure that you can get reliable data. So let's go back to this cross section here. The first question is, how many grids do you need? Because earlier on I said the key grid is in the middle, and that's doing this, ion discrimination. But you actually need a lot more than that to make a functioning sensor. So let me talk about the structure that these sensors need to work. So firstly, you obviously need an opening in the sensor to allow ions in. The top plate of the system should be quite robust. It should be able to survive, kind of harsh plasma conditions that can process it. For reasons I'll explain in a moment, it's also convenient to put like a nickel mesh grid against the aperture plate on the plasma facing side. I'll explain why on the next slide. Then, if you want to measure ions, you need to block electrons because you have both electrons and ions, and like you have positive and negative ions in the plasma. So if you want to measure ions only, you have to be able to block electrons. And if you want to measure electrons or negative ions only, you have to be able to block ions. So this first grid G1 here is meant to be to have a blocking potential to stop electrons to come in, or reverse the polarity to stop ions to come in and measure electrons. Then you need a discrimination grid. This is G2. I've already talked about that, which basically sweeps from 0 volts to some large voltage. And that's how we learn about the ion energies. We need to be able to measure the current, obviously. So at the bottom, there's a collector plate, and this goes to a current measurement circuit. And then one other consideration, which is more modern, when ions come in and they collide with this collector plate, they have enough energy that they're, the energy deposited is more than the work function of the material here. So that means that secondary electrons are emitted from the collector. And that would, currents, ions going in one direction and electrons going in the other direction, would add in terms of a current measurement, which would give you, incorrect readings. So what you need to do is you need to have a grid which suppresses any electrons that come up. So, this is usually set to some negative voltage with respect to the collector. So all electrons that come off just go back down immediately. And this gives you the cleanest data. So generally, you want to have 4 grids in place inside an RTA to make it work. So what are the other critical design considerations? So one thing is, in order to get good quality data, you have to make sure that no plasma gets inside the sensor. You don't want the plasma forming inside. You want the plasma outside and only measure the ions that are coming towards the substrate surface. So the way that works is there's this property of a plasma that's called the Debye length, and it's based on the electron temperature and it's based on the electron density. And essentially, the Debye length tells you something about, what can I say? Tells you something about how a plasma interacts with its surroundings, actually, and like how electric fields look over certain distances. Sort of long story short, you want to make sure that the aperture here, the aperture sizes, are less than a few Debye lengths. As long as you do that, plasma will not form inside the sensor. Plasma won't be able to leak inside. Just an example calculation here for 3 eV plasma, so that's like the electron temperature, which is pretty typical. Plasmas are typically in 2 to 7 eV range in terms of electron temperature. And a plasma density of 10 to the 17, which would be sort of, semiconductor plasmas are typically 10 to the 16 to 10 to the 18. So this is sort of middle of that range. That would be a 40 micrometer Debye length. So that means that, this aperture here needs to have a plate or a mesh behind it with the spacings of this grid like less than maybe 80 microns. So in the sensors that impedance reduce, we use about 20 or 30 microns distance there. That prevents most plasma from getting. What else must you consider? So in order to measure like what an ion energy really is, like that hits your substrate, you want to make sure that, so you can imagine the top plate of this is representing your substrate, and then you're going inside the sensor. The ion must be able to go from the plasma through the sensor, through the discrimination grid, without having any collisions. Because if there's any collisions, you distort the ion energy measurement. So that means that these sensors have to be very, very thin. Because if they're too big, they will, a particle will collide as it's passing through here. Because this is not obviously an absolute vacuum. This is at the same pressure as your chamber. It has lots of neutral gas in here from the chamber. So you must make sure that the mean free path of ions are larger than the distance between the surface of the sensor and the discriminator grid. Now, after the discriminator grid, if a collision happens, it doesn't matter as long as we collect the charge on the collector plate. So that means typically this is really on the order of like less than a millimeter, a few hundred microns. So here's an example. This is a charge exchange collision cross section. What that means is an argon ion, let's say, hitting an argon neutral, okay, and then they can, exchange the charge. This has a really, really large cross section, compared to other. Like this is kind of a worst case scenario, really. So say if you want to take a measurement in a 100 millitorr plasma, that mean free path works out to be about 0.5 millimeter. So that means that this distance here would have to be less than 0.5 millimeter in order to get a good measurement at 100 millitorr. These are the kind of things you have to think about. And this is also suggesting that these sensors would be limited in pressure range, because once you go above a certain number, the sensor gets, too small to work with. What else must we consider? So as I mentioned, we need to make these distances very, very small. But the problem is, depending on the gases that are present, you want to avoid getting arcing in here, because if you want to measure ions 1000 eV, 2000 EV, you have to apply very large voltages on this grid with respect to the other one. So you don't want to get breakdown happening inside here. So you can work out what's needed here. You look into what's called the Paschen curve. So the Paschen curve is basically on the x-axis, it's the pressure times the distance, and on the y-axis it's the breakdown voltage. And here's curves for different gases. So you can see here, for example, argon has a really low, the lowest breakdown voltage here in a certain range. So argon plasmas are very easy to strike. Whereas something like helium, requires a much larger breakdown voltage, and the ideal situation is at a higher pressure than at argon, or a different plasma, like electrode separation. So these are harder to strike, So you need to make sure that these distances are still big enough and you're within an acceptable pressure range, such that you don't have breakdown inside the sensor. The other things you do is you can add in insulating materials, on the edges here to prevent breakdown along the sides. That's typically what we would do. Kind of the next most important consideration is the filtering. So if you want to measure, RF biasing is very important for etching applications, by different frequencies. You obviously don't want RF, going from here to ground and loading your chuck and burning the sensor, or in other words, affecting the plasma. There's another consideration as well. So like, if you place one of these RFBAs inside a plasma chamber on top of the the bias electrode, you want this to not impact the plasma, okay? And that means what you want is that this thing has infinite impedance. You want to make it so that it's invisible to the RF, like it's not loading, it's not draining energy from the plasma or anything else. Now, of course, it's impossible to have infinite impedance. Well, I'll talk about that later. But in general, with a system, it's impossible to have infinite impedance. But what you need to put in place are these high impedance chucks. More than 100 kilo ohms or a few hundred kilo ohms is usually enough to make sure that you don't, load the chuck too much, that your data is still representative, and that you protect all the measurement circuitry from RF. So usually these chokes are actually placed in a feed through thing, so the vacuum interface. So no RF, exits out to the measurement electrons. But once these are in place, it means that you can actually take these ion energy measurements when an RF bias is being applied to an electrode. So let's go on to probably the most interesting topic for everybody, which is typical ion behavior. So let's start simple. So what do the ions look like in a chamber where the bottom electrode is grounded? And this also is pretty much true in a chamber where the bottom electrode is floating. So let's say you normally apply RF to the bottom, but the RF is turned off. So that means it's a floating electron. Okay? So what happens is the following. Your plasma sits at some sort of plasma potential, usually some small positive voltage with respect to the chamber ground. So kind of 15 to 25 volts, or this sort of range is very typical. So that means if the electrode is at 0 volts and the plasma is at plus 20, let's say, then that means ions will accelerate out of the plasma and hit this with 20 eV energy. So 20 volts, one charge of 1 E is 1 E. So when there's what we call a DC sheath present, you get a single peak of ions. And this is sort of a data example. So the idea is that it's sitting on a grounded electrode. All your ions have some sort of distribution, and the center of this distribution is pretty much the plasma potential. Well, actually, maybe the upper end of the distribution is the plasma potential. So say, for example, if there are collisions in the sheath, if the pressure is high enough that there can be a collision before you reach the sensor, it will, on average, bring the energy down from the plasma potential. But let's say in a perfect vacuum or ideal situation, all the ions will be, centered around the plasma potential. Okay, so that gives you information about the plasma, which is quite valuable. Just to give you an idea of what these sort of ion energy levels mean, like, depending on the material, let's say if you're doing deposition and you're depositing a polymer or something, maybe you need the plasma to do the chemistry, to produce the polymer that you want, or to activate the surface of the polymer sticks to it or something like that. You want actually your ions to be as low as energy as possible, because above a certain energy, they're going to start breaking the material that you're depositing, or they're going to start etching the material away. Like even sort of a 15 EV for something as soft as a polymer, for example, or some other similar materials, you're actually going to start etching and sputtering it away, or damaging it in some way. Or a more extreme example is if you want to etch through like a dielectric material, and it's a very, very hard material, you're going to need super high ion energies. But of course, the way you achieve that is not by just having a grounded electrode. You have to put a bias to it. So imagine if instead of this is being grounded, you have some DC bias, minus 20, minus 30, minus 40. Then the resulting ion energies will be, the plasma potential plus that bias. So it might be 20 plus, and then there's like another 30 depth, so your ions will get 50. And it'll still be a single peak. Let's look at something a bit more complicated. So let's look at the ion energy distribution function for RF sheaths. So let's say now your electrode is powered by RF. Okay, that means, so this just take a look at this diagram here. The red line here represents the RF versus time. Okay, and then there's the plasma potential, which is basically this blue dashed line on average, but in reality it's shaking with the RF being applied. That gives you a much more complicated situation. What's happening is there are times when the RF, the sort of voltage difference between the RF being applied and the plasma potential is quite low, and in those cases you're going to get low energy ions. And there are other times when the plasma potential and when you're on the negative part of the RF cycle, you have a very large voltage difference, so that's going to produce higher energy ions, and then you have everything in between. So what ends up happening is you end up with this more complicated distribution. We call this like a bimodal distribution or peak splitting, where now you have a whole bunch of ions at one energy, a whole bunch at another energy, and some distribution in between. And the shape of this is complex. It will depend on the pressure you're at. It will depend on the mass of the ions. It obviously will depend on the frequency. So this is the equation over here with everything. But if your RF is oscillating more slowly, the ions have more time to react to the differences, and the peak splitting is worse or larger. Worse or better, depending on your perspective, but it's larger. Or if the frequency is very, very high, the ions can't react. So on average, they just see some DC potential, and you have almost no visible peak splitting. But here's some sort of fairly typical data. I think this might have been 2 megahertz. So you have your high energy ions, your low energy ions. In this situation, the pressure was high enough that the plasma was sort of collisional. So these 2 little peaks you see here, in black, are actually echoes of these. So this is cases where ions are traveling through the sheath, had a collision, lost some energy, or gave passed their charge onto something that was stationary or practically stationary, and so there's a momentum difference. So then you have these like little peaks based on those collisions. So these are like the sort of 2 extremes of what you measure. So again, if you have any questions, just put them in the chat, and then later we can come back to them, in a few minutes. So let's dive deeper again. How do ions behave in different conditions. Okay, like more than just these two. Like, what happens if, for example, you have different pressures? Okay, so here's some examples of IEDFs different pressures for argon. These are all from published data, and afterwards, if people want copies of the full papers, just let us know and we'll send it to you. So you can see here at the lowest pressure, 7.5 millitorr. This is in a grounded electrode, 100 watts on an ICP. You had this nice energy peak of 7.5 millitorr. Well, as you increase the pressure, the energies were decreasing. This is obvious because of collisions, right? And the further you increase the pressure, the more that your average energy went down. And in this case, also the ion flux went down. So the ion flux is represented. So how many ions are impacting your surface every second is represented by the area underneath these curves. So as this area gets smaller, you are seeing less ions per second. So this, in other words, this would be like quite a significant decrease in etch rate. This would be maybe a factor of 5 decrease in etch rate by changing this pressure, not over a huge range. Let me show you another example for different gases. So under the exact same conditions, 15 millitorr, 100 watts on the top. For different gases, you get different behaviors. So in this case, the ion flux was highest for hydrogen. I suppose that kind of makes sense. Hydrogen is the lightest gas there. You're going to have the most particles per second movement, right? It's going to be most reactive to what's going. Whereas nitrogen, nitrogen is quite complicated because it has, it doesn't just get ionized, but it also has vibrational and rotational modes. So when you have gases like nitrogen present, it absorbs a lot of energy. Like when you have a pure argon plasma or pure, like say, helium plasma or something, a lot of energy is going into the ionization of the particles. But when you have a molecular plasma, you have a lot of energy also going into vibrational and rotational modes and so on. Not a topic for this talk, but maybe for another one. This is where pulsed RF and pulsed plasmas become very important because as a plasma is igniting, you have different energy modes happening. Like you have, absorption of energy into the rotational states, absorption into the vibrational states, and then like ionization, and then so on. So reactions take time as you ignite the plasma. And by changing the pulse frequency, so how long basically you let the plasma be on before you turn it off again, you're actually changing what chemistries can happen because you're not letting certain species form or you're letting certain species dominate in the first millisecond compared to the second millisecond. But anyway, that's for another day. Let me give you some more examples of pressure variation because I want to show that over a very small pressure range, you can have really dramatic differences. So this diagram over here, this is real data from our chamber impedance. This was 50 watts on the bias, 1.2 pascals, and 45 skims. This was argon, and that's a relatively low pressure. So you see this peak splitting is 13.56 megahertz on the bottom electrode, and then you see this. If you look over here, there's no ions here; it's flat. But over here, it's much higher. So this is a result of collisions happening between the electrodes and so on. So you actually have like this wide distribution of ions that have, their energy is being spread with the collisions, and then you have still two peaks available. And then just going from 1.2 pascal to 2 pascal, right? Which, okay, in one sense, it's a doubling of the pressure, right? But in another sense, like that's only a very small change in numbers. Now you have a much bigger, broad distribution of ions over such a small range. And then just going to 2.5, the structure, this peak structure is almost completely lost. And now you have ions, the energy is evenly spread over everything from 0 to the, to the maximum twice, the maximum energy. And then just going to 3 pascal, like just half a pascal up, now ions are mostly low energy and a lot fewer are high energy. So, let's say like if you go get your pressure gauge recalibrated and it comes back and it's off by 0.1 pascal, you could be going from, totally different distributions. This also is important why you have to monitor for like air leaks and stuff, because this small change makes a big difference. So yeah, maybe while these graphs are up, I'll just talk a little bit more about the measurements here. Over here, it's maybe a bit hard to see, but this is the average electrode voltage. So in other words, when you apply RF to an electrode, as I showed earlier, you have this RF on the bottom, you have the plasma potential, but the RF is kind of pushed down by the plasma potential. What I mean by that is the average, you end up with what's called a DC self-bias on the electrode that you apply RF, and that's usually some large negative voltage. So in this case, there's minus, the electrode is at minus 215 eV on average. So that'll be the sort of average energy that the ions see pretty much. Although in this case, the actual measurement of average energy is lower because the collisions are pushing it lower. So these ion energy analyzers can also measure what this DC self-bias is as a function of different conditions, which can also be important. Next, let's look at top and bottom electrodes. So what happens if you change the power on the top electrode? So this is a case where it's an ICP system. So everything is kept constant except the power on the coil at the top is being increased. And it's kind of what you expect. The ion flux increases. Okay, so the number of ions that are available to do your processing increases. So this would increase your etch rate or increase your dep rate. But the energy doesn't increase that much. Like the energy here is going from maybe 20 to 30. So this is basically an elevation of the plasma potential. Okay, but it's not a huge increase in energy, but you get a big increase in flux. So this is why ICP tools are important. In ICP tools, you can independently control the ion flux, and then I'll show you now, independently control the ion energy. So this is now, the top is constant, but we're changing the power on the bottom of where the substrate is sitting. And with no bias power, you just have a peak at plasma potential pretty much. And then as you increase the power, you're increasing this DC self-bias, right? So now the electrode is getting more and more negative. And for small increases in power, this is only going like up to 60 watts in this tool, you've had a huge increase in ion energy. You've gone from maybe 20 up to over 300 being available with a relatively small power. And maybe a bit hard to see here, but in general, the area under these curves stays the same. So as you increase this power, you're pretty much the same ion flux. You just have higher energies. So therefore, in an ICP tool, you can independently control the energies by changing the bias power, and you can change the ion flux, which is basically like etch rate and so on, by controlling the top power. Yeah, this is also where pulse plasmas come in. Like especially in a CCP tool, things are more coupled. So you can't independently control the top and bottom in a CCP. So you have changes in ion flux and ion energy with power in a dramatic way. But this is where with pulsed RF, it's quite important because by changing the duty cycle, you're changing how long, like what the average energy is. So let me put it another way. The 60 watt situation, which creates this type of plasma with this sort of energy. Maybe it creates the right chemistry for you, it creates the right energies for you, well, blah, blah, blah. If you then pulse that and you change the duty cycle so that now the 60 watts is only on 50% of the time, you're producing the same plasma when it's on, but the average ion energy is decreased. Okay, so you can create the correct plasma, but change the ion energies by changing the duty cycle on a pulsed RF system. Yeah, and you can go even more complicated. I can show you data examples later of using not sinusoidal waveforms but pulse waveforms. One other thing that's important here, this measurement here is 60 watts. Chances are that was like a generator output measurement. But your matchbox is not 100% efficient, and the matchbox efficiency depends on the plasma impedance, and it depends on the temperature of the match. It even depends on the wafer that's in the tool, because different wafers have different capacitances, therefore different, takes the whole RF circuit a different load. So it's really important to actually measure the power delivered after the matchbox, because like if your match efficiency changes, you can actually dramatically change your ion energy. Like you can see here, going from 0 to 4 watts added a huge amount of, like, really changed the ion energy. So imagine if your your matchbox is heating up and becoming less efficient, and now 8 watts is being delivered, this is really shifting down. Okay, just to sort of highlight the importance of really measuring the plasma. And actually, the next webinar will be on doing these measurements after, like doing these RF measurements after the match, of the power and what sort of effect that has, and the impedance and so on. Bias frequencies. We're getting close to the end. So what happens if you don't use 13.56 megahertz? What happens if you use 2 megahertz, 400 kilohertz? What happens if you use 60 megahertz? Why do you use different frequencies? This graph, I think, tells the story pretty well. And the higher the frequency, the less chance the ions have to react to the RF voltage going up and down in its cycles. So at really high frequencies, it almost looks like the electrode is, DC sheath. You get this sort of single peak. And then as you go to higher frequencies, lower frequencies, the ions can react more and more to this RF movement. So it kind of sees this sheath oscillating, it sees the electrode voltage oscillating. So you start getting that bimodal splitting I mentioned earlier. And as you go to lower and lower frequencies, like this goes down to like 500 kilohertz, you can get really wide peak splitting. So there's actually, this is advantageous, especially for etching. Like when you want to etch through the dielectric material, you need really high energy ions, and you need to sputter them, you need high energy ions. But if you wanted such high energy ions at 60 megahertz or whatever, you would have to put in a huge amount of power to get the DC voltage that you want in the electrode. Whereas if you use a really low frequency like 400 kilohertz at a much lower power, so these are all at the same power, at a much lower power, you get much higher energy ions. So by using 400 kilohertz, you can get the huge ion energy you need to do your process without, needing 90 kilowatts into your tool and melting the wafer or burning the tool. Now, this is in a simple situation. There can be more complex situations. So like sometimes coupling of the frequencies changes in a tool. So this is data from magnetron sputtering, 2 meg, 13 meg, 27, 40, and 60. And the behaviors are all over the place. And this is because in some tools, you can actually be in a capacitive dominated mode, or you can be in inductive dominated mode, and it can be quite complex. So usually, you can model this, but it's better to just measure directly using design. So we're nearly at the Q&A section. I just want to introduce, where can you use these things? So for example, where can you use an RPA? And in general, the majority of semiconductor processing or typical industrial processing plasmas are applicable. So DC, CCP, ICP, ECR plasmas, and deposition ones like magnetron sputtering and high pins and PCVD is fine. Various etching tools are fine. Thrusters and ion beams are fine. The only place you can't really use them is where, let's say in a fusion plasma, where it's just too hot to put an instrument. In very, very highly reactive plasmas, like maybe a high temperature CVD, where the grid structure and the materials and so on can't withstand the high temperatures, like 400 or 500 degrees Celsius, or above certain pressures. So once you get into the like tens of torr range, the sensor would just have to be so small it's impossible to meet. So below like 1 torr is kind of pretty much applicable for RFPAs. And I've sort of hinted all along, there's many applications like measuring deposition processes. And I want to highlight, like we have a special sensor that I'll show in a moment that is specific for deposition processes, for etching processes. You can measure electronegative plasmas, ion beams, measure thrusters, and many, many other things. And we actually have publications, hundreds of publications spanning all the different type of applications that you have. Just to very quickly then, I want to introduce that, obviously impedance has a range of these Semion, the RFEA sensors, and the Semion is our main product. And here's a picture of one in a plasma tool here. So you can see a big wafer on the inside of the chamber, and this is the vacuum feed through, and then this is going to the measurement electronics. Now, because we're low on time, I want to get to the Q&A. I'm going to skip through this section fairly quickly. But the data I've been showing you so far is taken with a Semion system. And if you have multiple sensing elements on one of these electronic wafers, you can get these real-time contour maps. And this sort of data takes about 1 second to 2 seconds to take. So you can very quickly change all the process parameters and get an idea of what's happening inside your tool. So, put it in one day, over a few hours, do all the different powers, pressures, gases, and so on that are relevant to you. And at the end of the day, you have your tool fully characterized. Or you can use it for escalations or something you want to see what's going on with a tool, or even match different tools. Make sure you have the same IUDX. And I want to show that there are different versions of RFEAs. We have one called the Quantum, but just to focus on it on this diagram here, you may be familiar with quartz crystal microbalances. So they're things that measure deposition rates that you can put inside a plasma tool. We can actually do a hybrid between this RFEA technology and a quartz crystal microbalance technology. And that means you have obviously all these ion energy and ion flux measurements, and you get the deposition measurements. But because you have this discrimination grid, you can actually choose to measure ions or not. So that means you can see the impact of ions on your deposition process. So you can see, what's my ionization ratio or ion neutral ratio, or ionization fraction, whatever you want to call it. And this is pretty critical for process transfer. So we have publications we can share afterwards that are like, if you match this ionization fraction or ion neutral ratio between different tools, even with totally different geometries, so like an R&D tool and an industrial tool, by matching this number, you actually get the same results with different tools. So this is like process transfer. Or there's other things you could look into, like, how does can I improve my results by changing the frequency? So here's examples of 2 meg, 13 meg, 27 meg, and 60 meg, totally different materials and structures depending on the frequency you use. And that's all related to the ion flux and ion energies that are present. So again, all this are our papers we can share afterwards. The one other special application I want to mention before we go into the tool section, you can modify these a little bit for deep etching applications as well. So let's say you're etching and you want to dig a trench, and the trench has a 20:1 or 40:1 aspect ratio or something. How ions are at the surface are obviously going to be different to how ions are at the bottom of the trench. And it's really important that all your ions are going straight down to dig a straight down, vertical trench. You don't want to have, sidewall effects. So by adding what's called a capillary plate to the sensors, you can change the aspect ratio of the sensor, the acceptance angle of the ions, and you can actually look at how many ions are making it to the bottom of a trench. What are the energies of those? What's the ion flux of those? And then the difference between what makes it to the top of the trench and the bottom of the trench. So you can see in data here, black is like the top, blue is the bottom. The difference is what was lost to the walls. So this is even kind of giving you information about ion angles. So, I'm skipping through all this quickly, but if people are interested in this, send a message. We'll do a one-on-one with your company or whatever, and really dig deep into the sort of things you can do with these sensors. They can give you real insight into processes without having to use lots of test wafers and lots of tool time and whatever. You can get very quick detailed information with these things. So I'll skip ahead a bit. There's also time resolved ones, and you can also look at positive and negative ions, and you can look at electrons. And the other thing I want to mention is, I mentioned earlier that you couldn't have an RFEA with infinite impedance, but you kind of can. Impedance have developed a product. It's not released, but we've actually developed it. It works in our lab. It works very well. It's passing all testing. We've developed a wireless version of these sensors where you can so that means that you can load in these electronic wafers into your tool through the load lock without having to break the tool open, So they can go in, think of it as like you have a bucket with 25 wafers, this could be the 26th wafer, and it can absolutely, in an absolute scale, qualify the tool. Are my energies correct? Are my ions correct? I've just done a PM. Is my tool the way it was 2 weeks ago and it was working well, So we have one of these sort of battery operated things where everything is built into the wafer. So release of this is, I'm not going to say imminent, but it's in the not too distant future. Again, if you're interested, please get in touch with us. So now I kind of want to go to the Q&A. I still have a lot of slides, but the idea is I want people to say, okay, I have a tool which is like this. How do your ions look in my tool? And I'll try my best to answer and try to give you an example. I just want to say, we do have data published in commercial tools like AMAT tools, Oxford Instrument tools, SEMES, and other ones. We've lists of hundreds of publications of what frequency we're using, gases we're using, what tool type, what pressure, and a link to the publication. And we have a copy of all the papers. So if you want to really dig deep into how things look in my tool, get in touch with us. We'll send you a copy of these application lists, and you can have a look.
Thanks, Tom. We have some questions coming in already, but could I just say that I know throughout the webinar we've had a lot of people joining us, and what I could say is that all of what you've seen here today will be sent on to you, the slides that Tom is sharing, and also a recording of the video. So please continue to send in the questions, and I'll read them out here for Tom, and we'll try and get through as many as we can before the top of the hour, which we're hoping to finish. So thanks again, Tom. It was extensive, and I know you could keep going for another hour.
Definitely.
If we had the time. So it's one of the first questions I'm seeing here is, can we use the same potential for repelling primary electrons and suppressing secondary electrons? That is, can we short these grids and bias it to a very negative voltage of -100 volts, which may be sufficient for suppressing both plasma electrons and secondary electrons?
Yeah. So like in what we produce, what we make typically, you can control what blocks the ions coming in from the plasma, and the one that the ions that come from the the electrons that come from the collector, we just use a fixed -10 volts to block them. But we have produced button probes before where we've tied the G1 to the G3 so they can be equal, and that means you can set whatever voltage you want on them. But generally we found from experience that the G3 grid, which is the one that controls the secondary electron suppression, that can be very, like, -10 is usually enough to deal with that. But you could tie them together, it would be fine, yeah.
And can RFEs be used for measuring energy distribution of the background charge exchange thermal ions in an ion thruster plume?
Yes, actually. So I kind of skipped past it, but if I show you, or maybe this data is not the best. For thrusters, so we actually have an entire section on our website on taking data from thrusters, and I have data later I didn't get to show, but we have our sensors have been used to characterize thrusters, which are then tested in orbit. Okay, so we're quite proud of that. But using one of our sensors called the Semion PDC, you can actually take measurements when like a plasma is on and plasma is off, and the plasma is off is obviously measuring the afterglow. So if I kind of talk you through this, the plasma is on, it's ramping up, you have all the ions at a certain energy. Or no, sorry, this is off. Yeah. Oh, okay. So when the plasma is on, as it's striking, the energies are getting higher and higher versus time. And when the plasma is off, it's decaying. Yeah. So this slope down here is the afterglow. So with the time resolved Semion PDC, you could do that. As long as there's enough ions there to get a decent measurement signal, that's fine. And what I didn't mention earlier in the RFEA construction is you can actually use different transparencies of those grids. So you can actually make the sensor more sensitive, or you can increase the collection area. So if you want to measure like a remote plasma or something with a very low amount of ions, you just have to make the sensor sensitive enough to get good signal to noise ratio. Likewise, if you have a very dense plasma, you have to tailor it so that you're not taking in too many ions. Yeah, I hope that answers the question.
Okay. Should the first grid of RFEA be grounded or floating?
The first grid needs to be attached to the chassis. It needs to be attached to the body, and it should not be grounded. So the idea is, this is actually quite important, and I'm surprised I didn't cover it. It's an oversight, and I have too many slides to go back. Well, yeah, way too many slides to go back. But basically, it's really important that the top grid of the sensor is at the same potential as the body. Okay, and that body is then connected to your electrode. So the idea, now, when I say connected, I just mean sitting on it. I don't mean I don't mean physically connected, like screwed on. So as long as there's an electrical connection, like the whole idea is that you want to measure what your wafer sees. So if you apply a bias, you want to make sure that the whole sensor goes to that same bias, or if the electrode is grounded, that the whole sensor is grounded. So we actually use that G0 grid as our reference to what the electrode is, and that's where those electrode voltage measurements come from in the data I was showing. So yeah, it must be connected to the body, and that body must be able to make an electrical contact with the electrode in order to get data that is representative of what your wafer would actually see. Yeah.
Okay, so to what extent does the applied RF power affect the ion energy in RF plasma chamber, assuming the pressure and the distance between the electrodes are kept fixed?
Yeah. So I'll go back up to I think I kind of answered this in an earlier slide then, but if I go into this, here we go. Yeah. So like as you apply different powers, you basically increase your ion energies, and that's effectively it, assuming everything else is constant. Can you repeat the question actually, Declan, to make sure I got it all?
Okay, so to what extent does the applied RF power affect the ion energy in RF plasma chamber, assuming the pressure and the distance between the electrodes are kept fixed?
Yeah, so essentially you generally increase the ion energy as you change like the power, but it also depends on the frequency that you're using and these sort of things. Yeah, I think I've answered it. Like I think this graph actually answered that. But like how much it does, there's a kind of a rule of thumb actually. The DC bias is typically about half of the peak-to-peak voltage applied. So if you apply 2 kilovolt peak to peak, your ion energies are probably going to be around 500 eV on average. So that's kind of the rule of thumb. But to be honest, if you use like different area electrodes, like 100 mil to 300 mil, and different pressures and so on, these all also have an impact. It even depends on your RF network and what your capacitances are and so on. But as a general rule, this graph here is true.
Okay, I think I have this one here. So how low energy can an RFEA measure?
It actually depends on the voltage supplies. Like ultimately, what we call energy is really, the voltage applied to the grids. So the ones we build, we use power supplies which are capable of 0.1 volts. So that means in principle you can get 0.1 EV resolution. So that means you can go to 0, 1, 2, like you can start at 0 and go up in 0.1 steps if you wanted and measure ions at energies that low. You can also scan around 0. Now there's a few questions on how to interpret that data, but you can scan around 0. There is generally a distribution of ions, that you could see around there. But the one thing I'd say is from simulations of RFEAs, like the electric fields inside them can be a little bit bent, or they can be a little bit like complicated, like not exactly uniform. So what that means is in reality, your resolution depends on the quality of how you've built the button. So if you kind of just throw a button together, your resolution is going to be no better than 1 EV, even if you use 0.1 steps. Like it's not, in terms of an absolute value, I wouldn't trust it, but in trends I would. But yeah, like 0.1 is not unachievable, let's say. 0.1
Okay, question here, Peter. Do radicals produced by the plasma have any effect on RFEA analysis? Can they be accounted for at all, given that they are neutral?
Yeah, that's a tricky one. Again, in some slides I've not shown, there are other components of the plasma that can impact the data. But there are three things actually that can impact the data. So one is, neutrals, picking up charge from the collector plate. You can have radicals interacting with the collector plate, like that's measuring the current. You can also have, like, say, ultraviolet that is being emitted from the plasma, like say a hydrogen plasma, like whatever, they're all emitting lots of ultraviolet. If the energy is high enough, you'll also be producing secondary electron emission with those, But the good thing is those effects are constant. So what they generally do is they cause a constant offset in the data. And because the analysis, you measure the IV curve, but then you take the first derivative, that means that any constant offset is gotten rid of by the derivative, right? Because if you take the derivative of a constant, it's 0. So that means that as long as let's say the UV flux that was constant over the scan, then the resulting data you get is clean because the derivative takes it out. So the analysis actually helps remove that. There have been people who have tried to control the situation to try to tease out information about, UV or about these things. And I know there's a thesis on it somewhere that I could share. But yeah, that's my answer. It
Okay,
can potentially have an impact, but minimal. Yeah.
This one is specific to slide 16, Tom. It says in an ECR plasma, we sometimes measure ion energies, which are negative, like the one you showed on slide 16. Do you know how to overcome this artifact?
Ion energies that are negative. Well, what that could be is actually that there's electrons of high enough energies, or if there's present of magnetic fields in an ECR, that there's electrons that are by collisions making it into the sensor. So actually, I think increasing the electron repelling potential might help there. Assuming the person asked this question has a Semion, be aware that we have a support@impedance.com. And if you email that, there's a team of scientists who will answer. Like, we all have PhDs in plasma physics and years of experience using these things. And we tend to be quite responsive, like within a day or two, you'll get an answer. So if you have these sort of questions, you can email us. And especially if you have our sensors and have a data file, we can give you a lot of input based on that. Sometimes it's even just the settings. Sometimes there's something subtle in the settings that can actually make these artifacts. But my first guess would be higher. You need to. Not all the electrons are being removed. Like, most of the electrons sit around 0 eV. Like, if you do a negative ion scan, you basically get the electron energy distribution function, going backwards around 0. So it might be actually interesting if you do a negative ion scan and see, is your artifact similar in shape to what you're seeing in the positive ion. And again, if you contact us, we can send instructions on how to do a negative ion scan with these systems. It's just basically reversing the polarities. It's not too hard to do.
Okay, so this again is specifically to a slide on the slide 21. What is the difference between ICP power and bias power?
Sorry. So in an ICP tool, I have a diagram which later, but in an ICP tool, you have a coil on the top, and then you have a flat electrode at the bottom. So here, ICP power is power applied to the top coil, and bias power is power applied directly to the bottom electrode only, if that makes sense. So whenever I say bias power, I'm talking about power applied to where the wafer sits, and top is just to the other side. Yeah.
Okay. Could you speak briefly about pulsed sources, the effects, how they affect the IEDs?
Yep. That data I was showing a minute ago. So actually, on our website, we have an entire presentation called Semion measurements and pulsed ICP systems. And it has lots and lots of cool data examples. And if you can't find it on the website, email us, we'll send it to you. But in a pulse system, it depends whether it's pulsed on the top or on the bottom. So on the top, as I mentioned, you get data like this. If you look in a time resolved way, what happens is, in general, pulsing reduces, depending on the duty cycle, right? Pulsing reduces the average ion energies that you see, and then the frequency is controlling the chemistry. But this is kind of what you see in pulsing. But this is like the negative ion scan and positive. It would actually be better if whoever asked that question, share your contact details afterwards, and I'll send you a special set of slides that just give data and papers and references for pulse ICP systems, or pulse systems in general. The pulse bias has a different behavior than the pulse stop, obviously. Yeah.
Okay, so how can we extract the ion density from the EDF plot?
I have a slide at the very, very end of slide 50, so I'm afraid to scroll all the way to the back, but let's see if we can get all the way to slide 50.
Yeah, again, we can reach out specifically if
yeah. So this is how you calculate the ion flux. So basically, it's the area underneath this curve. What was the question again? Sorry. How can you extract the ion density?
How can you extract the ion density? Yeah.
Yeah. So that's an extra step. So first, you measure the ion flux using the positive scan, okay, and then you do that negative ion scan I mentioned, and the negative particles around 0 are the electron energy distribution function. So from that, you get the electron temperature. So then with the ion flux, the electron temperature, and then using an equation then called like the Bohm velocity equation, you can actually tell what the plasma density is. directly above where you took that measurement. Now that won't be the plasma density in the center, but I suppose what people really care about for processing is the plasma density right above the wafer. So yeah, ion flux, do a negative scan to get the electron information, use the bone velocity equation, and that is going to give you the plasma, the ion density in the plasma.
Well done, Tom. Questions on the spot. Listen, as we've reached the top of the hour, and I know we're trying to keep it to the timing. Thank you very much to everybody who attended today. And as I say, we will be sending out all the details here again, including the recording. But please, feel free to keep sending us questions, or if you want to reach out and we'll set up a specific consultation with Tom or other members of the team. So thanks again, and we'll see you at the next webinar next month. Thanks a lot.
Thanks, everybody.